Number 6. Oh, this one's going to be a little more tedious, but and number 6 is given the thermodynamic data for the synthesis of ammonia, where we're taking the reaction is nitrogen gas plus 3 hydrogen gas in equilibrium with 2 ammonias. Okay, and you're given delta H non-formation is 0, 0, minus 40, 5.9 kilojoules per mole. And the entropy, notice there's no delta there. And that's the way it always occurs in the standard thermodynamic tables. And because of Nernst's heat theorem, which states, what is Nernst's heat theorem again? It's the fourth law that for any perfect crystal at 0 Kelvin, there's 1 microstate. And the entropy is kV times natural log of omega, which is the number of microstates, which the natural log of 1 is 0. So for every perfect crystal at 0 Kelvin, there is 0 entropy. And that means that at temperatures above that, we have a non-zero entropy. And so there is no 0 entries in the entropy. The standard thermodynamic tables are all at 25 degrees Celsius. So we have 191.6 joules per mole K and 130.7 joules per mole K and 192.8 joules per mole K. Okay. So part A is find delta G naught for the process. Okay, and now we're going to have to take advantage of what is, we know that the Gibbs free energy is equal to what?
Delta H minus T gas.
Yes. And so now all we have to do, and this is the tedious part, we got to find both delta H naught and delta S naught. And please pay attention to the fact that the entropy is in joules per mole K and the enthalpy is in kilojoules per mole. So those are the two main traps to avoid when it comes to the calculation of this. So delta H naught is equal to, what again is delta always? Final minus initial, so it's product minus reactants is going to be equal to 2 moles of ammonia times minus 45.9 kilojoules per mole of ammonia. Minus 1 mole of nitrogen and 0 kilojoules per mole of nitrogen, minus 3 moles of hydrogen at 0 kilojoules per mole of hydrogen. And I know it's kind of silly that I put those up there, but this is going to be the same format we're going to follow when we go to calculate the entropy. And so it's just good practice. If you just pointed it out that this was it, I would accept it. Because we have a finite amount of space. That just using these 2 moles and neglecting those because they're 0. But if you can find the room, at least on the scratch paper, you have the room. So that's going to be equal to 2 times 45.9, so I gotta go.
91.8.
Thank you. Equals minus 91.8 kilojoules per mole. And now delta S,
Is it just kilojoules? Because you got rid of the moles?
well, yeah, I'm going to bring the moles back when
Okay.
we talk about the overall process, because it's it's for every mole of reaction. Okay, and without any loss, I just kept the moles here as a bookkeeping.
Okay.
Now, delta S naught is going to be equal to, again, 2 moles of ammonia. In this case, it's 192.8 joules per mole of ammonia per K. Minus, and it's going to be 1 mole of nitrogen and 191.6 joules for every 1 mole of nitrogen. Okay. Minus 3 moles of hydrogen times 130.7 joules per mole hydrogen. Okay. I could have put the K's up top, but it made it a little clearer, but I just had it. Anything will do. And that's going to be equal to something. I'm going to have to get my scratch paper out. And I'll work it out over here real fast. So at this point, this is really a bookkeeping problem at this stage. And it's, that's the tedious part. And actually, if you make an arithmetic error here, I'm not going to care very much. That's why I wanted this explicit information. If you make an arithmetic error, at this point, you're going to get most of the credit, because I'm more interested in the setup than the actual answer. It's the most relevant part. And so, 192.8 times 2 is 5 times 2 is 18. 2 is 385.6. And 191, okay, 130.
It's 392.15.
Oh, the whole thing?
No, the 3 moles of 130.7 is 392.15.
1.5, and that is going to be added to 191.6.
392.1, sorry.
Oh, 92.1?
Yeah, the J was looking like a 5.
Oh, okay, Jerry's looking like a 5. Okay, 6 and 1 is 7. 2 and 1 is 3. 9 and 9 is 18. 3 and 2 is 583.7. So it's ultimately going to be equal to 385.6 joules per mole. Okay. Minus 583.7 joules per mole. Okay. And now I can erase my scratch paper. I know I'm going to go back to my scratch paper for a second and do that actual calculation. So 583.7, 385.6, 1. 13 subtract 5 is 8. That's 9. That's 498.1. So now,
The change in S is negative 190.
yeah, well, the delta S. So back on the page, I have delta S is equal to minus 198.1 joules per mole. Okay. And this is why I had to bring back the mole per mole business. Is now we have to do another calculation, which is ultimately delta G naught is equal to delta H naught minus T delta S naught. So I have to convert delta H to joules per mole, so it agrees with either that. I can convert delta S to kilojoules. I prefer to do it convert it to joules, and so what's that? Minus 91,800 joules per mole. Minus, and now what is the standard temperature?
298.
298. If you wanted to, at this stage, round that to 300 for an approximate answer, that's 2 degrees. I'd be more than happy to accept that because of the shortened time frame that's allowed in a test. But we can go ahead and do it the 298 Kelvin times minus 198.1 joules per mole. Okay. Now we have to dust off some scratch paper again. So bring lots of scratch paper to the test. If not, we'll provide you with some. And I gotta multiply this whole business. Let's just do 300. In the interest of expedience, because I don't want to burn that much video time. Yeah. But I'm making an executive decision here. I'm going to do it at 300. It makes life a lot easier. Minus 198.1 times 300. That's 0, 0. 3, 8 times 3 is 4, 29 times 3 is 27, 29. 1 times 3 is 3 inches, 594. And now I've got, okay, so this is equal to minus 91,800 joules. I'll put a little squiggly line, it's just about equal to that. A minus is plus 59,430 joules per mole. And then I just got to do 91,800 minus 59,430. 0, 7. 7 subtract 4 is 3. 11 subtract 9 is 2. I think 32 equals. Minus 32.37 kilojoules per mole. And I went and switched it back to kilojoules to make life easier for the next part of the problem. So that answers, what was that, part A? That was a lot for part A. Now we're going to get to deal with part B.